So we formulated the problems, and now we're going to solve them in Excel. And when you solve these problems in Excel, you're going to need a special add-in called Excel Solver. That's what we're going to learn how to use today. And I have instructions on how to follow through, which is part of your notes. But what I'm going to do is I'm going to do it on Excel itself, and you're welcome to do that or follow through with the notes. I would recommend doing it in Excel. So if you go to the eCampus, there should be a file on there in the content area under this. So if you go to the course content, click on the lectures, the lecture notes, and go to modeling. You should have the Excel lecture companion file that you can download, and then you can open it up to the first tab, which is the wire products class tab. And that's where we're going to start by building up our, yes? So go to the wire products file, because that's a nice way to do a variety of different things. So if you're still downloading the file, let me know once it's done, okay? So when everybody has that. Now, if you're using a Mac, you're going to have to download a separate solver, because Mac does not have Excel Solver built in. So, do you have Parallels? Okay, Parallels allows you to use a Windows emulator, so you can run Windows on your Mac. So, I'll show you how to do that, but for the time being, just use the lab computer. So if you have a Mac, then just use the lab computer for the time being. I can show you how to do it on Excel, on Office for Mac later on. And again, which version of Mac Office are you using? 2014 or 2010?
Whatever one comes free with university.
When?
When I started here. So
Okay, so that's 2010. So that's a separate Excel solver. Now the current 2014, I believe, has got it built in to the actual Excel database. So okay, the actual Excel data tab.
I have 2016.
Yeah.
Okay, you have 2016?
Yeah.
Okay, then 2016 should have it.
Even on a Mac?
I have the simulator on my,
Well, we're not all privileged, Jake.
I downloaded my CS101. That's still it.
The Windows emulator.
This will take 20 minutes to open.
Where do you upgrade this guy?
Huh?
Where do you get you that upgrade with the Start Best menu?
I would appreciate it. I'm just gonna try and make it through college, man.
Hit that tax refund.
I got my W-2's fucked. I gotta go get my W-2 fixed.
Oh. Like when you get W2.
Yeah, they said I only made $800 and I made like at least $3,000.
What?
Where did it come under?
Here we go.
They closed. Beanery is closed.
And then
So we
So
should-
it's like I'm kind of fucked. I gotta go try and talk to the one on Evanston.
All right.
see if they can look in the course.
So is somebody still not downloading the? Is somebody still not got the? Is somebody still not got the file in here? All right, so everybody's got the file. So if you go to your data tab, now those of you who just did it on the Mac, you probably have it, so you don't have that problem. So this question mark with this arrow, that's the solver tab oh, that's the solver command. Does anybody have it on their data tab? Okay, so most of you will not have it. So in order to insert it, you have to go to File, and I can't see this over here. File, and then go down to Options, and then go to Add-ins. Okay, so is everybody with me here in Add-ins? So once you're in Add-ins, then click on, right at the bottom it says Manage Excel Add-ins, and just click on Go. And then there's this add-in box that's going to come up. Make sure that you have the solver add-in checked. So check the solver add-in check mark box. And once you've checked that checkbox, so for me it shows up right at the bottom here. So once you check that, then just click OK, and then you should see just Excel installing it. Okay? So once you click on the checkbox for solver add-in, and you click OK, yeah, so the Mac, if it's 2016, then you can, do you have to download it? Or it should just,
hit tools and like add.
Sorry, you should just,
Okay, go to tools and then go to Excel add-ins.
This is all of them you checked or just that?
just the solver add-in. Just check solver add-in. So once you check that and hit OK, you should have the add-in. So you go into your data tab, and you should see the solver add-in, this question mark with the arrow. Okay? So once you've added that, then just click on solver, and this is the menu that it should open up. Okay? So by default, whatever was the last cell that was selected, it's going to set that cell as the objective cell. Okay? As our objective. So we want to point to the correct objective cell. So we're going to get to this a little bit later. I want to start by how do we build this problem in solver first. So we know how to get solver now. So how do we build this problem? So if you remember, we first wrote the formulation out, all the equations, the objective function, the constraints, and then we put it into a Tableau. Remember that? The matrix format. This is exactly what we've done over here. So on the top, we've listed all of the decision variables. Remember our decision variables? Insect screen, industrial cloth, insect screen, roofing mesh, and snow fence. And then below it, we have the coefficients of those decision variables for the objective function as well as for the constraints. Now there's one addition over here, that we have a column called actuals. Okay, I'll get to that in a minute. Then we have that column that shows us what is our relationships, and we have that max or min to remind us what our objective is. And then we have the right-hand side values, RHS values. So that is how we set up our solver in Excel. Now the formulas that we have to put in, we start with in what we will use as our objective function, and let me see if I can expand this a little bit. Yeah, that's expanded, but I can't see how I. Okay, so what I have here is a formula called sum product. Does that show up in your file as well? Yeah. So the sum product file, the sum product formula has as its inputs 2 rows or 2 columns of data, and those 2 rows and those 2 columns have to be equal in size. In other words, in this case, the 2 rows have to have equal number of columns in both cases, so there are 4 columns each. And what the formula does is it multiplies the first column of one row with the first column of the second row, and then adds it to the second column and the second column here, the product, and adds that product to this product, and so on. So it takes the sum of the products. That's why it's called sum products. Okay? So it takes the products and then it sums it up. So what's going to happen is, as the algorithm is running, there are values that are going to be included in those blank cells, and then those values are going to be iterated through the different steps of the algorithm until we get the optimal solution. And as we cycle through each iteration, you're going to see a calculation which is going to calculate for us, in this case, the total profit, which is the number of 1,000 square feet of each of these products times the profit, which is added up over there in that function. Then, in the same way, we also have the constraints. So in this case, it's the number of hours. Remember, it's the number of hundreds of hours of machine time, Y machine time in this case. So again, it's the coefficients multiplied by the decision variable values. Now, if you notice from your formula, I have anchored the decision variable row with dollar signs. Those dollar signs allow me to, for example, if I wanted to pull this down, then even though this cell references row 4, when I pull it down, it continues to reference row 4, because those dollar signs anchor that formula only to those particular cells. So that is how you set up your actual values. So these are the values that are actually going to be used by the solver algorithm to calculate what the optimal values are. Then the right-hand side is just exactly like you would get from the Tableau function or the Tableau format, which is your right-hand side values. Okay? So that's how you set up your linear program in an Excel spreadsheet. Any questions about this? So I'll just go through a couple of different examples. So we have the computer scheduling problem. So you remember the computer scheduling problem, right? So for each constraint, there was basically just M11, M12, M13. So in this case, we just have ones over here. And then we had greater than or equal to, and then the right-hand side values. And in the objective function, we had just those 3 contract prices, which remain constant throughout all of the different periods of time, right? And over the top, we had all the different objective function, all the different decision variables, 3 decision variables for each month. If you want to go in further, you can look at the Lego simplex problem, where we have the decision variables. Now notice that I've always highlighted the decision variables in red, because you always want to make sure that that's where you anchor your dollar signs. Okay? Then you have the 3 constraints, you have the actuals, you have the constraints, the relationships, and then you have the right-hand side. Then we'll do this problem next class when we do integer programming. This is the transportation problem. Wait, this is not the this is the slick oil problem still. Okay, so the transportation problem is right here. So again, we have the 6 decision variables. We have our objective, we have our actuals, our relationship, and our right-hand sides. Okay? So pretty straightforward. That's how you set up all of your. Once you set up your Tableau in Solver in Excel, then it's very easy to go into Solver and set it up, as I'll show you now. Okay. So now that you've set up your, and I strongly recommend you highlight your objective function box. You set up your Tableau like this, where you have your objective coefficients, you have your constraint coefficients, your red is marking your decision variables or your changing cells, and then you have your right-hand side values. Now, you will notice that I have labeled all of these items, and the reason I'm labeling them is Excel Solver actually uses those labels when it spits out different reports. Okay, and those reports are really useful, as I'll show you. Okay? So let's take a look at these. Any questions until this point? Remember, it's critical because you have to do this for your homework day after tomorrow, okay? All right, so let's call Excel Solver. So we click on that command, and to set the objective, we're just going to click on this box, and I'm going to set that cell as my objective, right? So cell G6 is my objective. Everybody got that? So our objective is G6. So all I have to do is click on this right-hand side collapsing box over here, and then click on G6 as my objective. Now, I know that I want to maximize, so I want to set my objective to the maximum value. Now you can also choose minimum, or you can also set the value to a certain value. I want to set it to a value of something. All right, so you can also do that. But we are interested in the maximum profit, so that's our maximum. We can do minimum. In the transportation problem, for example, it will be a minimization problem, so that will be minimum. And here is by changing cells. Now that's where we have now the red highlighted cells. Okay, so we go in, we click on this collapsing box here, and we click on our red highlighted row of cells. Those are all our changing cells, our decision variables. So once we've done that, we expand that box again. So we've done our objective, we've set what our objective is, we've defined our decision variables. Now the next step is we have to set up our constraints. So I'll show you a couple of different ways to do the constraints. So the one at a time way, oh, why is it? Okay, I think I set that up twice. Okay. So I want to add my constraint. So the one at a time way is the cell reference is my actual. So for the Y machine, I'm going to set that as my cell reference. Then again, the relationship is there to remind me. So there's a variety of different relationships. So the first one, when you drop down this middle relationship box, you'll see it's less than or equal to, then there's equals to, greater than. Then there's also, you'll see integer, binary, and what's the bottom one? DIF. So you can have differential as well, which we're not going to get into. But integer and binary we're going to use from the Thursday's class. We're going to see how to formulate integer and binary problems. And that's the slick oil problem that you see. So right now, by default, the less than or equal to is what we want. And then we have the constraint, which is the right-hand side value, which is set up over there. So that's our constraint. So once we've done that, we can just say OK, or if we want to add another constraint, we hit add. So in this case, I'm just going to say add another constraint. Now, what I can also do is I can also add more than one constraint at a time, especially if whenever the relationship is the same. So now in this case, the relationship is the same. So I'm going to add these two constraints at the same time. Of course, I could add all three constraints at the same time. So I'm dragging. Now make sure that when you're dragging, the size of the left-hand side, the cell reference, and the size of the right-hand side, the constraint, have to be equal, as well as they have to have the same cell reference numbers. So you have to start, say, in this case, we are starting with row 8 and ending at row 9. You cannot have the cell reference start at row 8 and end at row 9, and then the constraint start at row 7 and end at row 8. Okay? So that's going to throw Excel off, especially if you have large problems. And then, since we've added all our constraints, we can just say OK. All right? So now we've added our constraints. Now, you remember the variable restrictions? There's two ways of entering variable restrictions depending upon the type of variables that you have. So for integer and binary, we could actually include a constraint. You saw in the drop-down box, the relationship, there was an int. That's integer. when we learn how to set binary variables on Thursday, then we set another constraint for decision variables that are binary. Okay? Now, for non-negative, this is where you set up the non-negative variable restriction. You say that, what does it say? Make unconstrained variables non-negative. Okay? So that's how you set the variables to be non-negative. So this will always by default be checked. Now sometimes your variables can take on a negative value. So if you're doing, for example, you're trying to minimize your forecast error, okay? Your errors, your decision variables could be negative, right? So in this case, you'll uncheck that box. Now you'll also see that there's a drop-down box for the type of solver engine that you're using. So select a solver, what does it say, method? You say? Okay, so the solver method, so there's different types of engines you could use, solver engines. So the solver engine that we're going to use is a linear programming engine. It's called the Simplex LP. The Simplex is the basic algorithm for any linear program. And we are always going to use Simplex LP, except when we do inventory management. For inventory management, we are going to use the GRG nonlinear. Okay? So that's basically all you need to do right now to set up your linear program for solving. You set the objective, you define the decision variables, you set min or max, you add your constraints, you restrict your variables. If you're using integers and binaries, you have to set constraints. If you're just doing non-negative, you have to make sure that box is checked. And then you have to select the solution method or the solver algorithm. So in this case, we're using the LP simplex algorithm. Now, there are various options that you could choose, and these options you don't really have to get into. These are mainly used if you are going to be doing large-scale linear programs, large-scale integer programs, or non-linear programs. So we're not going to get into things like precision, automatic scaling, that's only used for non-linear programs. Iteration results, again, is used for large-scale binary and integer programs. So we're not going to get into that. This is only if you use nonlinear programs, particularly in terms of how do you want to conjugate your derivatives using forward or central conjugations. And this is, again, for large-scale nonlinear programs. You use evolutionary algorithms, which you're not going to get into in this class. All right, so that's basically the options. So I'm just going to hit cancel, just so you know what those look like, why they're used. You're not going to use them in this class. And in case you're wondering why we don't do a lot of nonlinear programming, really most of the world we can solve using linear programming. Okay, even I'm pretty close to trying to strike a deal even for the network design. Hopefully we'll get there. But the network design software is a linear program. Okay, most large-scale problems, because it's much faster to solve versus a nonlinear program. So once all that is set up, then all you have to do is hit solve. Okay, so go ahead and hit solve, and you should get a box that looks like this. All right, so it says over here, keep solver solution or restore original values. So sometimes you get an error box or a warning box over here, and you might want to restore original values, especially if you're solving in a step process. So we're not going to get into those large-scale problems. So we're going to always accept keep solver solution. We also have a bunch of reports over here. Okay, we have answer reports, and then we have sensitivity reports. So what I'll do is go ahead and select the answer report. So just click on it and select the sensitivity report. Whoops, not the limits. Okay, so just click on each one and select it. Now the limits report is used for nonlinear programs, so we don't want that, or large-scale integer programs. And then you click OK, and you'll see that there's 2 more sheets that have been added to your Excel spreadsheet. So go ahead and click on the answer report. I'm going to expand this. So as you can see, Excel has actually used the labels that I input to actually generate these reports. So IC, IS, RM, SF are decision variables. So we have something called a final value, reduced cost, objective coefficient, allowable increase, allowable decrease. We'll get to that in a minute. But the solution is always going to be here in this first column, the final value. The final value tells us what is the optimal solution for our problem. So our optimal solution says we have to produce 4,000 square feet of industrial cloth and 2,000 square feet of insect screen. Okay? And we don't produce anything else. So notice that the optimal solution is not maximum profit, right? The optimal solution is how much do we produce of those. So the decision variable is telling us our optimal solution. Now, you'll see that this is the objective coefficients. This is the values that we actually wrote into our formulation, right? That's the profit, right, for each of the decision variables. Now, notice that for these two variables that we produce 0 of, we have something called a reduced cost. Okay? Now, the reduced cost in this case is a little bit misleading. Each software has its idiosyncrasies. It's hard to write it commonly for everything. So in the case of Excel, Excel has written its reports for a cost minimization problem. That's why it's called and reduced cost is a term that is used in the formulation. So in this case, because we are maximizing our profit, right? Because we are maximizing our profit, the reduced cost, that minus 5.7 tells us that in order for you to produce roofing mesh, your profit margin has to go up by 5.7. So it has to go up to $9.5 before you start producing that. Does it make sense? So your profit margin has to go up by that amount because this is a maximum profit maximization problem. Similarly, your snow fence, the profit margin has to increase by 4 units. So in this case, it is $400, right? So we have to increase our profit margin by another $400. Now, we have the allowable increase and decrease. Now, remember I said for very large-scale problems, you get sensitivity reports. This is a form of a sensitivity report. The sensitivity report tells us how sensitive the problem is to changes in any of these inputs. And I'll get to this allowable increase and decrease in a second. I, by mistake, started with the sensitivity report instead of the answer report. So let's go back to the answer report here. So our objective, our actual tells us that our profit, if we use that solution, is 34. In other words, $3,400 is our total profit. We have our final value. You can see that the variables in this case are all continuous variables. And we'll go back to the sensitivity report and see what these mean by binding and non-binding. But just basically, what this means is that for those two constraints that have binding, that have the label binding, your actuals equal your right-hand side value. In other words, your right-hand side constraint is preventing the problem from increasing the profit. Okay? So you can actually increase your profit if you add more resources to your wire machine time and your loom capacity, your wire drawing and your wire machine loom capacity. So that tells us, and also it tells us that the aluminum actual is non-binding and we have a slack. In other words, we have a surplus of 500 weight of aluminum. So the aluminum is not binding the problem. We don't have a problem with the supply. So going back to the sensitivity analysis, we talked about these. Now the allowable increase and decrease over here tells us how much those coefficients can increase before the solution changes. All right, the solution will, if we increase the profit margin by more than 5.7, that solution is going to change. Okay, we're going to get a completely different solution.
So is that like 34 when the other answer changes, or like?
So the decision variables is going to change, which makes sense, right? So the allowable increase, so if you go more than that, then that's what's going to cause the roofing mesh to come in. So this is the solution right here. This is the optimal solution, 4 and 2. So clearly we can see that that's going to change. And again here the allowable increase is by 4 units, allowable decrease is by 1 unit before the optimal solution changes.
So that would correlate back to these?
Yes.
But if you change that by 4?
Yeah.
Okay.
So the optimal solution will change. In other words, what you produce is going to change, which makes sense because if we change that, then our solution is going to change. So in terms of the constraints, we have the final values, and you can see for the first two, the final values are 6 and 10, which is the right-hand side values. But for the last one, it's only 10, which is less than our right-hand side value. So now, for our binding constraints, you can see that we have something called a shadow price. But we don't have that for our non-binding constraint. We don't have a shadow price for that. What is the shadow price? Remember I said that those right-hand side values are constraining us? So the shadow price is telling us if we add 1 unit of that particular resource, that's how much our profit is going to go up by. Right? So our profit is going to go up by $400 if we add 1 unit or 100 hours of wire machine actual time. So that's an amazing amount of information, right? Because now we say, okay, is it worth that investment? Right away we can tell that. Of course, it's a really simple problem. But you take more complex problems, you get a lot more valuable information from them. And again, here you have, for your loom time, 100 hours of increased loom time is going to increase your profits by $100. And again, this tells you how much you can increase your wire machine actual time by and your loom actual time by. Now you'll notice that this 1e plus 30, that is, you can increase it to infinity or decrease it to infinity. Okay, so that's the meaning of that. Now clearly, you can reduce the profit margin to infinity, to negative infinity. It's not going to change anything, right? Similarly, you can increase the amount of aluminum hundredweight that you have on hand. You can increase it to infinity. It's not going to change anything in the problem, right? So that's the allowable increase. So let's do some simple tests of this, just so that we can confirm that these are true. So, for example, I want to increase my profit margins by $400 by improving my wire machine, by increasing my wire machine capacity. So I go in and say, let's increase this from 600 hours to 700 hours, right? So this should, according to the sensitivity analysis, increase to 38 or $3,800, right? So let's call solver and ask solver to solve the problem. So just click on solve. And this time we're not going to check any reports. We're just going to say okay, and you can see that that increased to 34. So now my allowable increase in terms of the loom actual is 2. So if I actually increase the loom capacity from 10 to 12, will this increase to, so right now it's the optimal for 7 over here, but I changed this back to 6. So this should go back to 34. So it should actually go back to 36, all right? So by increasing the loom capacity from 1,000 hours to 1,200 hours, for each 100 hours I add, I'm increasing my profit margin by $100, okay? So you can play around with these things and see how this helps you in not only solving the problem for the optimal solution, but also understanding the other piece of information that you can get from it, right? So I have some more information that we can go through as it pertains particularly to the sensitivity analysis, and I'm going to use the Lego problem, since that's what we were working on, as an example. Before we go on, is there any questions we have over here? So, do you want, let's do something else. I think that is of some value before we do this. Let's go in, and why don't you go ahead and so there's two tabs, the transportation problem solved and the transportation problem. So I believe, okay, so the transportation, go to the transportation problem tab and try to set that up using Excel Solver. Okay? I think it's of value that you can try to do it by yourself here in class so that we can actually see. So if you want to set up an integer constraint, I'm going to show you this once we do integers as well. If you go to Solver, then you'll see what I've done over here is I've highlighted all my decision variable cells, all the changing cells, and in the drop-down box, I select int, integer. So what then Solver does, it says these values should all be equals to integer. Okay? So that's how I set up. Now if you have binary variables over here, like we're going to learn how to do binary variables in the next class, all you have to do is go in and highlight the decision variables that are binary, bin. Okay? And for binary variables, you do the very same thing. So on Thursday, we will learn how to do a formulation of a binary problem. And we have binary variables. And you do the same thing as you would do with any of the other variables. You have the constraints over there, and you would have any objective function coefficients, and you just add them in as another variable. Okay? So the binary variables are just added to the tableau like any other decision variable, and their coefficients for their respective constraints and objective coefficients are set up. Yeah.
So for the homework, do you want us to work through the problems like we learned, like on paper,
Formulate them, yeah.
and then put it in here, but only submit the Excel?
You'll have to submit the Word document as well.
Okay.
Yeah. Yeah, so the Word document you can just put X1, you don't have to do subscripts.
Okay.
Just do X11, X12, right? So just,
like the table or something.
yeah. Or you can just write it out, you know, the objective function, whatever, 24x11 plus 20, you know,
Yeah.
so on. You can also use the equation editor if you want to learn something new. Okay, so let's look at so we have a couple of minutes over here. So first let's go into the notes, and I want you to write down the formal definition of each of these sensitivity analysis components.
The definition for a little long. Yeah. All right, small boy.
So everybody got this? Nope. Got it? Right. So, so I'm going back to the Lego simplex problem here. And I have my decision variables, the actuals, the objective function, the objective coefficients of profit, and this is for the military one. If I set up my solver, then I have the objective function, I have the maximization, I have the changing cell setup, and then I have the constraints. But I also have to add the integer constraints for the changing cells, right? So these two have to be integer values, right? So I add this as an integer. Of course, I solve it. Now, what you'll notice when I solve it is I don't have a sensitivity report. So the problem with solver is that we don't have a sensitivity report to tell us what our reduced costs are, what our shadow prices are, what our allowable increases and decreases are. So in that case, what we have to do is we have to actually go in and manually change those values. Okay? So I've given you some exercises that you can do. So the sale price of table, we have a couple of minutes, we can do one or two of them. So the sale price of tables is increased by $2. Okay? How much does the military solution and the public solution change? So in other words, we have to go in actually and we have to set it up and say, okay, so sale price for tables goes up by, what did I say, $2, right? So this changes to 24. So what happens when we do that? We solve, and now we make 0 tables and 4 chairs. Oh, hold on. Hold on. I made a mistake over here. I changed the wrong one. So I have to go in and change the sales price over here to $63. And now resolve it. So nothing changes. The optimal solution does not change. I still make 2 tables and 2 chairs. I do the same thing for the public and see what happens. Okay? So for the public, it's 57 and 37. So in this case, I would put 59 and 37. And I still make 3 tables and 0 chairs, but my total profits increase to $27. So unfortunately, when you have integer problems or binary problems, then you have to go in and do this by hand. So I've also given you some examples of when you can set up the number of small blocks, the number of large blocks, increase or decrease by 2 2. So the number of small blocks is decreased by 2, number of large blocks increased by 2. So remember when you were solving this by hand using the blocks, I said, okay, last minute I can say, okay, you have to take out 2 blocks. Those of you with me at BCO 199, I did the same thing. It kind of throws a wrench in the works because you've run through the solution and now you have incomplete information. So this is a quick and easy way, even though it's cumbersome in the sense that you have to actually go in and change values. Very often what you'll have is, if it's a very large problem, you'll have a large flat file, a comma separated values file, a tab text file, or just a simple Excel file that you can upload with all the changed values and resolve it. The problem is you cannot do it in a short period of time. The sensitivity analysis allows you to make those analyses take place in a short period of time. Any questions? So play around with this, work on these problems on your own so that you get a little bit of familiarity with this method and with the solve.